Hi class, I'm still not feeling all that great, so I'm going to do another video lecture for today.
Now, it feels like we've had a lot of new material thrown out there really quickly, so I think this might be a good time just to pause and do a very quick recap. So, electric charge has a symbol of Q, and it has units of coulombs, which has a symbol of C. Electric charges can be positive or negative. The fundamental charge is 1.6 times 10 to the minus 19 coulombs. Electrons are negative of that charge and protons are positive of that charge. So charges can be positive or negative. Electric field, that's got a symbol of E, is the electric force per unit charge. So that tells us that if we place a charge Q in an electric field, it's going to feel a force. Good things to know here is that electric fields and forces are both vectors. Electric field has units of newtons per coulomb. Electric force is a force, so it has units of newtons. In our equations, we say that electric field is the electric force divided by the charge, or the electric force is the charge times the electric field. That's good too. Often when we're doing problems like this, we have to layer in the fact that the net force that acts on an object is mass times acceleration. So you can't throw away Newton's second law. Okay, so that's fields and forces. We also know that charges in electric fields, not only do they feel forces, they also have electric potential energy. Electric potential energy has a symbol of a U, that's for potential energy, and E for electric potential energy. Electric potential energy is a scalar, so it's just a number, and it has a symbol of J for, well, not a symbol, it has units of joules, and joules has a symbol of an uppercase J. Our expression for electric potential energy is charge times field times distance from the negative plate. E here is the magnitude of the field, and S is distance from the negative plate. Electric potential is the amount of electric potential energy per unit charge. Electric potential has a symbol of V and units of volts. Electric potential energy, we just said, was UE. Electric potential is also a scalar. And electric potential, let's write down that relationship. So V is the energy per unit charge, so the energy divided by Q. And on the flip side, electric potential energy is charge times potential. Both scalars, and we've got our units mentioned. The last thing is we can combine the latest two expressions we wrote down. Energy is Q times E times S. Energy is Q times V. That shows us that electric potential and electric field are related. This one is a little bit dicier because fields and potentials, the electric field is a vector. The electric potential is a scalar, so we have to be pretty careful about that relationship. What we know is that the magnitude of the electric potential is the magnitude of the field times how far we are from the field. And then the other thing we know is that electric field points towards low potential. When we combine those two ideas, what we get for a result is that our x component of electric field is minus delta V over delta x, or delta V is equal to minus EX delta x. And our y component of electric field is minus delta V over delta y, or delta V equals minus EY delta y. Okay, hopefully that little summary will help keep you on track and give you a place where all of this electricity stuff is all in one slide. Next, we'll be ready and move on and do some examples.